In the last video, I worked on the reset circuit, got it dialed in, and enjoyed some stability there. I got into the clock circuit and got to the end of the video, discovered a very messy ground, and rather than getting into a long troubleshooting session, I punted that into this video. So today I want to try to dig into the ground and try to figure out exactly what's making that so messy, pun intended. And I also have some issues that are preventing the clock from working properly. I want to debug those, get that all working properly. And I'm going to start pushing towards another PCB order so that I can start building out another large section of the 16-bit computer from scratch. All right, let's start digging into this. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. My wife Carrie has been working on a cookbook. Carrie's cookbook provides a unique culinary experience by seamlessly incorporating doTERRA essential oils into a diverse array of mouth-watering recipes, transforming ordinary meals into extraordinary dining adventures. The cookbook offers a treasure trove of innovative dishes that combine the health benefits and aromatic richness of essential oils with fresh, wholesome ingredients, making gourmet cooking accessible and exciting for everyone from novice home cooks to seasoned chefs. Each thoughtfully crafted recipe not only tantalizes the taste buds, but also promotes an overall well-being, harnessing the natural potency of pure essential oils such as lavender, lemon, peppermint, and basil. In Carrie's cookbook, she emphasizes the quality, flavor, and simplicity, guiding you through detailed, easy-to-follow instructions with beautiful photography and expert tips. Whether you're looking to elevate your everyday meals, explore new flavor horizons, or embrace a healthier lifestyle, Carrie's cookbook is your ultimate guide to enriching your kitchen and your life with the magic of doTERRA essential oils. If you are interested, there's a link in the description. Okay, here's the circuit as I left it in the last video. Now, it's been a few days. Let me remind myself exactly what the problems are here. This is in reset. The copy looks like it is complete, but it's not stepping. It looks like it's supposed to be in single step mode, but it really should be in the adjustable clock mode. I cannot get it into the high-speed clock mode or basically out of the single step mode, but I do finally make it into running mode. There's some low-hanging fruit here. So let's start with this break signal. The break signal is supposed to put this into single step mode, which is this third LED here. I have the signal extended to the interface point, but I'm not driving it. I don't have it hooked up to the control ROM mid plane yet. And so I need to do something with this particular signal. The easiest thing to do at this point is to tie this low. Let's see what that does. So now I have the adjustable clock working. I can bounce back and forth between the high-speed clock and the adjustable clock, but I still can't get into single step. The next piece of low-hanging fruit is this single step button. It was supposed to be pulled low, which it is, but then when you press the button, it's supposed to be driven high, and that is not the case. That's driven low. So if I replace this with a connection to 5 volts, let's try that again. Now my 3-state latch is actually working properly, but I am not getting any, but it finally makes it out, but I'm not sure what's taking it out of reset. The adjustable clock is responding to the single step. I don't know what the high-speed clock is responding to. The single step. And the single step is not responding to anything. I've got the logic probe out. The clock is actually presented on pin 6 here of this OR gate, and that's high. Pin 5 is always high. Pin 4 is always low. It's not oscillating at all either. Pin 4 is coming from pin 3 here on this AND gate. The AND gate is driven by the output from the latch, which is oscillating. but it's ANDed with the inverted step select. Well, the step select is on this upper portion of this NAND gate, and if I trace this signal down, this is the set, not the reset. The LED down here is not on, therefore that signal is not on. That should be this signal over here on the right, which is high. Okay, well, let's give this a try again. Pin 4 is now oscillating. Pin 5 is still high, which means that my output here is still high. Okay, the step clock and the step select are supposed to be ANDed together on this AND gate up here. The step select is supposed to come from this NAND gate. So here's the input here on pin 13. Pin 13 is supposed to be connected to pin 11 here. It is not connected to pin 11, it's actually connected to pin 13. So this blue signal here, this blue wire here, is too short. It needs to be extended by 2 positions. Okay, let's reset. That appears to have worked. What do I have coming out here? I'm oscillating. Okay. Single step is causing an oscillation. Adjustable is causing an oscillation. And my high-speed dividable clock is not causing an oscillation. Could that be floating? So my counter is not counting properly because I did not tie the up signal high. So now that it is tied high, that's now oscillating. My high-speed clock is, divided high-speed clock is coming out here now. That is working as I thought it should now. All right, nothing I'm about to say here is to be taken with any sense of authority. I am not an authority on this. I do not presume to speak from a position of authority, and if anything, just consider everything that's about to come out of my mouth absolutely wrong here. I'm learning. What I'm trying to articulate is what I think I know, and not anywhere close to based in fact. Well, it's pretty much that way with all my videos. Okay, let's talk a little bit about this ground issue I've got. So I am taking ground down here on this bottom rail and comparing it to ground up here right at this crystal oscillator. My power or voltage does come in here at this connection point. So I'm about as far away from that as I can get down here. And I'm measuring it against the ground that's being supplied to the crystal oscillator. And I realize just how bad this measurement is going to be and how this particular long ground lead is going to create all kinds of measurement issues. So what I observe might really actually be a measurement problem and not necessarily a ground problem, but I believe that there is something here to look at that could be cleaned up. All right, let me turn the power on here. And you can see just how much deviation that I'm getting. I'm at 200 millivolts per division, and I'm getting between 250 and 300 millivolts oscillation. The interval is 25 nanoseconds per division. I should be able to measure this with my time cursors. So about 30 nanoseconds, we're looking at 33.3 megahertz. I've got a 10 megahertz oscillator, so that's oscillating faster than my clock is. Now, is the clock contributing to that? Well, I tell you what, if I pull the crystal oscillator out, it goes pretty flat, and I've got just general noise. Definitely looks different than with the crystal oscillator inserted. So what can I do about that? If I take that as my baseline without the crystal oscillator and the breadboard, and I want to get as close to that as I can, I do believe that there may be some things that I can do to improve that. Okay, the first thing I want to try here is decoupling. I think I'm going to take this ground signal and extend it up here like that, and then tie that over to that ground rail. And then I should be able to take a 0.1 microfarad capacitor, place it across those 2 points. We'll see what that does. Okay, let's measure that. Okay, that provided a marginal improvement, but not significant. The next thing I want to try is, in watching Usagi Electric, many of the computer connections, interconnects that he deals with has the signal interleaved with the ground in between each one of those. I believe I can do something similar here by taking and dropping in ground connections in between each of these pins in an attempt to see if I can't isolate that signal a little bit better and provide a little bit better grounding around it. Maybe that will help. Maybe it'll make things worse. So let me add these individual ground connections. So that done, I can now drop the oscillator back in, and I've effectively got a ground plane underneath the oscillator and a ground plane that separates that from the digital logic. Let's see if that does anything. Okay, power. Not really. Not so much. I did get a comment on the last video that implies that the impedance of the clock and the wires associated with that were actually creating the problem on the ground plane. And I can test that by making this signal as short as possible, and I will do that by disconnecting my longest trace. So currently, my oscillator comes over here to this counter, and then from the counter continues onto the control ROM control module. So if I disconnect that from the control ROM, I am way down into very small signal changes. And then if I plug that back in, yes, indeed, it does come back. Now, I guess the question is can I improve this at all by hooking up additional ground connections to this PCB? Right now, I only have one that's coming from the breadboards to the PCB, and then it's chained off of the PCB to go down here. And can I add more ground? So if I was to, say, do something like this, will that improve it? And I did see a marginal improvement there. So there was before, and there's after. So is there a chance that all it is just a bunch of connections between the PCB and the breadboards? And ultimately, once everything's on PCB, I'll end up working better. The suggestion was to put a 33 ohm resistor in line of this signal at its termination point. Well, that's going to be over here on the control ROM control. And to add that would be I'm going to say a difficult thing to do. I am going to be reordering this board, so I will put in a place for it as close to its destination as I can get. But I believe I'm going to end up pulling off this crystal here anyway. So I actually have it built in already, thinking about it, because I've got a 0 ohm resistor on the back of this. If I was to solder in a 33 ohm resistor in its place, I don't have anything at surface mount of that size. But if I was to put a 33 ohm resistor in place of the 0 ohm resistor, that could effectively do that. The Relay Computer channel has a very good video on what I believe I am experiencing here. Having a 10 megahertz crystal oscillator on the board, I believe, creates a number of issues that are going to impact signal integrity. Now, for me, I'm not dealing with something as severe as what he describes at the beginning of his video, but I believe it plays into that. I'll leave a link in the description. Go check out its channel. It's a fascinating build. The best I can come up with is 3 100 ohm resistors, which are soldered together to effectively divide into a 33 1/3 ohm resistor. And my plan is to take this little wire here, which is from the 100 megahertz crystal going off to the counter IC, and replace that with this 33 ohm resistor. See if that actually gets me anything. Now, why would I do this end as opposed to this end? Well, the reason I would try to do that is because it's going to be a pain in the you-know-what to try to solder this on the back of that PCB at the moment. Now, I know I still have that other signal line dangling there, but let's give that a shot, and let me see how that works out. Okay, at 200 millivolts per division, I am looking at about 200 millivolts of noise. Compare that to pushing about 400 before that. On top of everything, this is still actually working. And as I reset, I perform the copy, and then everything shows up lit, which is my current test scenario as far as what my instruction register would be presenting. All right, let me pull the rest of this wire out here. All right, let's give that a go again. That looks to be about the same. 100 nanoseconds, there's 25 nanoseconds per division. So I think ideally it would be better to put it on this end. Now, for me to do this on this, I would have to remove a 1206 surface mount and replace it with a tripled up quarter watt resistor package. That might be a little fragile, a little bit difficult to manage. I'm going to call this a win for now, especially since things are working. Finally, all the way back in my video number 7, I talked about decoupling capacitors and tried to make sense of them for myself. It seems counterintuitive to me that we put a decoupling capacitor as close as practical to an IC's VCC line, and I still struggle with that a little bit to this day, trying to make sense of it. Now, I recognize that conventional wisdom is to do that and then connect it to ground as quickly thereafter. And in the case of these ICs here in the breadboard, I'm putting the decoupling capacitor directly across the pins and dropping them into the ditch of the breadboards. But I don't have the ability to do that with this 10 megahertz crystal. I have added a 0.1 microfarad capacitor here on VCC tied to ground, but that ground point is nowhere near the ground pin. Now, that distinction feels very significant to me. If you watch my video 7, I talk about not conventional current, but how the electrons flow and how taking a gulp of electricity ends up creating ripples in a ground plane. Now, again, this is the world according to Adam, so you must take that with a grain of salt. That does not mean that I know what I'm talking about, not even in the slightest. But intuitively, at least in my mind, this is the way I see things happening. So I struggle because it feels like the decoupling capacitor really needs to be as close as possible to the ground pin, not VCC. Comment below, let me know what your experiences are with this. So what I'm wondering is, if I add a 0.1 microfarad capacitor here, from the ground pin of the crystal oscillator to the 5-volt rail, effectively decoupling both sides of the power of this crystal oscillator. Is that going to make a difference for me here in how clean my ground signal is? Let's give it a shot. Now that peak to peak appears to have reduced a little bit further than the 200 millivolts I had before. If I try to slide this around a little bit, that looks like something maybe 150, 175 millivolts. It's not a significant improvement, but it is an improvement. I think I'll make that capacitor permanent. Next on the list is one final revisit to the control ROM control module. Now, I'd mentioned previously that I want to remove this oscillator here. And the reason for that is I've got a 10 megahertz oscillator that's going to be on the clock module that's going to feed this raw system clock directly. So there's no reason to have this additional component sitting here or its resistor in order to connect things. And then this resistor is going to end up being a 33 ohm resistor based on Laserford's recommendation. Let's run a quick rules check here. All clean. And now let's go update the PCB. Most of these are going to be removals, not adds, so I expect this to be somewhat simple to address, except for maybe some footprints that need to be updated. So here's a capacitor that should no longer be needed. And I've got a couple of traces here. All right, I've got one capacitor that needs to be removed. All right, this capacitor is still here, so which one is this? And which one am I missing? Now, the next thing is this is my 0 ohm resistor, and I want to move this to be a little bit more in the center. All right, let's try that again because that didn't work out quite as well as I thought it should. All right, let's run a rules check. Now I've got an opportunity to stitch the grounds back together a little bit. Yeah, I created some issues. The last thing I think I want to do is pull the silk screen from the bottom down here and put it up here. Yeah, maybe center that a little bit better. Finally, I need to change the version number here. It's technically the same interface pin-wise, but I'm changing the pin positioning, so is it version 2.0 or is it 1.1? I think this is a bug fix against the current interface points, so I'm going to call it 1.1. Well, I like success, and I'm going to quit while I'm ahead. I know this is a short video, but right now I am enjoying absolute perfect stability on this circuit as it stands right now. Even on the breadboard, the 10 megahertz clock is driving the control logic midplane perfectly. I'm getting good copies from the EEPROM into SRAM. And that's something I wasn't sure I was going to be able to get stabilized, so I'm very, very happy about that. Now that 10 megahertz clock, before it gets distributed, automatically gets divided at least in 2 to 5 megahertz. But then it can be divided by 3, divided by 4, divided by 5. So I can have a 3.33 megahertz, a 2.5 megahertz, etc. as it continues to divide all the way down. I am still pushing hard to get to the next midplane. Now on this midplane is going to be the reset circuit, the clock circuit, and I want to add in the fetch and instruction register into that midplane. So now that brings me to the next video. I am going to pull the fetch and instruction register off the old build and incorporate that into this build now. It worked pretty good, and I want to make sure that it continues to work, so I've got a little bit of tune-up to do on it, but we'll get into that next video. All things being equal, by the end of the next video, my hope is to be executing no-op instructions. That would be exciting. See you soon.